बात ज़्यादा कालरात student का शो बहुत अच्छा था।
जज़ाकल्लाह। क्या बात है।
मेरा नाम Walther Schewarzacher है। मैं physics professor University of Bristol में हूँ। Bristol Great Britain में है। यहाँ London बहुत मशहूर शहर है, बहुत बड़ा शहर, मुझे बहुत पसंद नहीं है।
क्या बात है क्या?
Bristol बहुत बेहतर है।
माशाअल्लाह।
छोटा शहर, जिंदगी बहुत अच्छी है। ओके, अभी मैं अंग्रेजी बोलूँगा क्योंकि मेरे लिए बहुत ज़्यादा आसान है। Okay, this is a picture of Bristol, typical UK city, by the sea, nice harbour, nice streets. So the history of the university, it is not super old by British standards, but the university was the first to have both ladies and men graduating with the same degrees. So it was the first in the UK to do that. And it has a very distinguished record, numerous Nobel Prizes in different subjects, as you can see here. I do not believe in rankings, and later on you will hear me say to you that you must be critical in everything you do. If there is one message from my talk, it is be critical. Be critical of your results, be critical of your professors, be critical of everything. In a good way, be critical of my talk, in a very good way. But if one says a little bit about rankings, the Faculty of Science, we have a lot of bureaucracy in the United Kingdom, and included in this bureaucracy, the government assesses research in every department of every research university, and by luck, or by more, the University of Bristol in science is actually in quality the top university in UK. Yesterday you were hearing about how Oxford became the top university. Actually in science, Bristol at the moment is better. So one thing I have to say. Okay, end of advertisements. Now I will say a little bit about my actual topic of this talk. I'm going to say something about a schematic picture of electrodeposition. In yesterday's talk, you had an introduction to electrochemistry. Electrodeposition is electrochemistry, but what happens is you reduce metal ions to form a metal, and you're interested in this metal. So imagine you have a positive electrode and a negative electrode. You apply a potential as shown, and the copper reduces and becomes copper metal. But here too, when you first form the copper from the ions, there is a nucleation phenomenon. So there is an energy barrier, and the size of that barrier depends on a number of things, including how much potential is applied. So again, we have to worry about the surface term and the volume term. Exactly the same as before. So here is a question: can we actually see the critical nucleus in electrodeposition? Well, the thing to do, and this is a really important message, if you want to find out whether an experiment makes sense or not, always do a simple calculation. It does not have to be a super sophisticated model. Sometimes now the fact that we have computers takes away from the fact we can get very good estimates just with pencil and paper. So I already showed you how simple the physical chemistry behind classical nucleation theory can be. Let's apply it to electrodeposition. So now we need the bulk term, which will depend on this quantity, which is the potential. And if I do the calculation, I get that it should be 3 by 10 to the 10 when this potential is in volts. So the contributions are potential and the number of atoms per unit volume, because the more atoms you have per unit volume, the more energy that you save per unit volume. Okay, so here is the area term. It depends on the number of atoms per unit area, just like the volume did for the number per unit volume. And it depends on other important things. You remember I said that when you create a surface, you have to do work. The reason you have to do work, in the case of the Oreo, is you are breaking the bonds and the connections in the icing. When you are creating a metal surface, you are also breaking atomic bonds, and the number of bonds will tell you what the energy is. And there are other important things to consider, like the latent heat of vaporization. So, what that works out is that if we put all those numbers in, we can say that the critical radius has this formula, and if we work it out for copper, very simple calculation. I didn't go through all the details, but you could see that it was a simple calculation. If I apply a potential of 0.1 volts and put the numbers in and use my phone to do the calculation, I get that the critical radius should be about 2 nanometers. So, can we see it? Not very easily. But this hasn't stopped people trying through experiments. This is, I think, a very interesting example. I have not put the reference because I'm not going to be very polite to this work. But what I will, I've put the reference but not the author's names. But what is important is where this is published. Nanoletters is a super high impact factor journal. It's one of the ones which people, if you get a nanoletter, you'll say, yeah, I've got a nanoletter, it's great. Super high prestige. The authors whose names I'm not giving, if I remember rightly, they are in Stanford in the US. So top university. And the result looks good, because you have the size of the nucleus here, and you have 1 over the potential. And if you remember I said, the simple theory says the size should be proportional to 1 over the potential. So great, they've seen something really exciting. But the key thing is the unit here. They are measuring things that they see with their microscope that are micrometer size. The critical nucleus is nanometer size. Therefore, their results are rubbish. The reason why I'm giving you this example is, first of all, that it is possible to do very simple calculations, and secondly, you should do them. If these authors had done a simple calculation, they would have realized that what they have published and publicized throughout the world cannot possibly be right. So please remember lesson number 1, do your simple calculations. And this applies whether you are first semester, second semester student, or whether you are a professor in Stanford University, or even Bristol. So, to show a few of our results, after nucleation of metal happens, then you start to get lots of little pieces of metal, and they compete to grow. And watching them grow is really quite interesting to see what is happening. And to do so, you need a microscope which has got good enough resolution. A scanning probe microscope is good enough for this. And we're very lucky in our university because there is a company nearby which has developed one of the fastest scanning force microscopes in the world. And here is an example. I speeded it up by a factor of 10, but only 10. even if you were to look at it in real time, it would still be visible. I speed it up, and I hope this will work on the computer. Yeah, you can actually see that it starts to grow.
Wow, nice.
The interesting thing is this grain. Notice that all around it, the material is growing, but this grain grows much faster than the other ones. And that was actually a surprising thing to see. If you do a cross-section, then you will see something that looks like this. Again, watch this peak, and you will see that it grows much faster.
Ooh.
So this is quite an interesting example of the application of nucleation, as it's something that I do research on and I'm interested in, but it can also be used to show the general application of this nucleation phenomenon. Another thing which I will mention that we do research on is ice nucleation by biomolecules. What do I mean by ice nucleation by something? Well, I said to you that there is a critical nucleus. You have to have something bigger than the critical nucleus to have the phase change. In the environment, you normally don't get the nucleus forming spontaneously just from water. It's helped by having something else there. And what is helping it is usually some sort of surface. And when you have nucleation caused by a surface, it's called heterogeneous nucleation. And basically what happens is this. By forming a nucleus on the right substrate, you can reduce its volume, because you can see that this hemisphere has half the volume of a sphere. If you choose a substrate where the nucleus is even flatter, then for the same radius, you can have a much lower volume. And the amount by which you reduce the energy barrier is just a ratio of the volume of the critical nucleus on the surface to the volume of the sphere. And of course that depends on this angle here. If that angle is small, then you have only a tiny fraction of the sphere. If it is 90 degrees, you have a hemisphere. So that angle is key. You would think that's ice nucleation solved. All you have to do is change theta. But it's not easy to change that angle and to understand how to change theta. So that's why we need to have model systems to study heterogeneous nucleation. And heterogeneous nucleation is key to what happens in many clouds. We actually use proteins to nucleate ice on. Why do we use these proteins? Well, one reason is that we had them in the laboratory, but a better reason is that they are highly symmetrical and therefore easy to model. And remember what I said, physicists like simple things. They like to hide the simple things by using complicated mathematics. And some of the mathematics is genuinely complicated, and the phenomena behind them is really complex. But if you can make it simple, you should. So here is how we do the experiments. They're very, very easy experiments, except for the fact that you need access to liquid nitrogen. Well, you could cool the material using just a Peltier coolers. You don't really need the liquid nitrogen. Anyway, what we do is we have a sample, we have a microscope, and we have a way of cooling the sample. The sample is just droplets of water. And here you can see a selection of the droplets of water seen through the microscope, and they have frozen here. And we do our experiments to measure the time at which the liquid water droplets become frozen ice droplets. We make these measurements at a fixed temperature, Hence they are called isothermal measurements. And we measure what fraction of the ice nuclei are unfrozen as a fraction of time. And if you plot that on a logarithmic scale, you get a graph which looks like this. And it's possible to fit this graph using very, very simple statistics, so-called Poisson statistics. We use a Poisson distribution for which we only need two parameters: the mean number of nucleating agents per droplet and the nucleation rate. And so we can get, with just two parameters, what is really a very good fit. And so here is our result. That is the mean number of nuclei per droplet, and that is the freezing rate per nucleus. So, are you impressed by that?
Very much.
You should not be. Why? Because you should never, and I mean never, ever, 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 quote so many significant figures. This is a very simple model. What that means is that nothing beyond maybe the pharmaceuticals, food, for freeze drying, also for energy technology. I know that Professor Walther's research area also involves the nucleation of materials to save solar energy. So it's important for technology and also for the environment. Here's a picture of the sea ice in the Arctic Ocean, and ice is also important on mountains with snow. But there is also interesting physics here, because all of you, I'm sure, know that at atmospheric pressure, the temperature at which ice and water are in equilibrium is 0 Celsius. Basic high school science. But what is a little bit surprising is that if you have got small droplets of water, they can remain liquid down to temperatures like -40 Celsius. So you can have supercooled liquid water at very low temperatures. And this is important because clouds consist of small droplets. So where the temperature might tell you that you should have ice in a cloud, actually you have water. And why is that important? Because apart from producing precipitation, clouds are very important for the energy budget of the planet. Because you all know about the greenhouse effect. It's a really bad thing to put carbon dioxide into the atmosphere. But it is also a bad thing, in some cases, to have the wrong kind of cloud. Because clouds do some good things. They reflect light back off from the Earth. And that's good. It stops the Earth from heating. But at the same time, when longer wavelength radiation comes up from the Earth, it's reflected back. That's the greenhouse effect. Light comes in at short wavelength, is emitted at long wavelength, and is then reflected back. It cannot escape. Carbon dioxide is bad in that respect, so are some clouds. And whether a cloud is a good, friendly cloud or a bad cloud depends on the size of the water droplets, and also whether those water droplets are liquid water or ice. So what that means is understanding what happens in clouds, and in particular how water droplets become ice, is not only really interesting physical chemistry, but also very important for understanding climate change. So why doesn't ice always form at 0 Celsius? Here is the reason. It's down to this word nucleation. Nucleation is super important when you have got a first order phase change. Going from liquid water to solid ice is a first order phase change. Nucleation is important. Nucleation, in the case of ice, is forming the very first bit of ice. So here is a physicist's picture of ice. A physicist likes everything simple, so I am saying that the ice crystal is just a sphere. The sphere has a volume and it has an area. If the radius is r, then the area is 4 pi r squared. High school maths, but enough to explain some really interesting science. Because every time you create a surface, that requires energy. How many of you know Oreo biscuits? Hopefully everybody.
Yes, sir.
So here's an experiment for you, and you are allowed to eat the Oreo afterwards. Take an Oreo biscuit and pull it apart. What are you doing? You're exerting a force over a distance. Force times distance is work. So to pull an Oreo apart takes work. But what are you creating? You start with a sandwich. When you pull it apart, you've created two surfaces. And that seems a really simple explanation, but it is still correct. Every time you create a new surface, you have to do work. And the same is true for the surface between solid ice and liquid water. And the energy that goes into it is proportional to the area. There is also a saving in energy. It's free energy, which is proportional to the volume. If there was not a lower free energy for ice than water, you wouldn't get ice. Many of you will have studied thermodynamics so much that you hate the subject. I want to persuade you that thermodynamics is actually your friend. It is something which is much, much, much more interesting than most people really think. It's not as nasty as it may first appear. So the free energy is saved for the volume. Here is some simple maths again. The total free energy which is in that ice nucleus has got a positive term, which is proportional to the area, and a negative term proportional to the volume. Here you are again. Surface, positive, volume, negative. And this is a really simple graph. If you plot it for small r, then I think it is clear that this will dominate. Because if you take, say, the number 0.1 and square it, it's 0.01. Cubed, it's 0.001. The square is bigger than the cube for small values. So the curve looks like this. It starts off increasing, then here the cubic term comes in, and it decreases rapidly. But this positive part is the energy barrier. That is what stops the liquid water becoming ice. There is this energy barrier. And what that means is that somehow you have to spontaneously form clusters of ice, and only if they form with this size of radius, then they will grow spontaneously, because as they get bigger, their energy will decrease. So this is what causes your problems. It's actually very unlikely that ice will form spontaneously with a large radius. What happens is, as you go to lower and lower temperatures, this radius decreases, so the ice becomes more likely. That's the physics of it, and it's the basics of what is known as classical nucleation theory. So, in this 5 or 10 minutes, I've taught you really all that you need to know about a new topic of classical nucleation theory. So, that is the expression for the energy barrier. We can find what the critical radius is, by doing differentiation. Since this is supposed to be a lecture that is enjoyable, not hard work, we don't have to do differentiation, but this is the answer. The radius is inversely proportional to how much energy you save, and this is the value of the energy barrier. Okay, so that's nucleation theory applied to ice. I believe in kindness. Tell them don't. So that is what I should have said. But also remember my first lesson. Always do an order of magnitude calculation to check if your results make sense. That was ice nucleation by a protein solution. I know the concentration of the protein. I know the mass of each protein molecule. So I can work out that there are around 10 to the 12 protein molecules per droplet in this experiment. So how can the mean number of nucleating agents be 3.7? If I were to publish that result, it would be like the result from Stanford I showed you before. It is meaningless. So, if you get a result like that, you really have to think a little bit what's happening. And what we think is happening here is that the protein, biomolecules can form clusters, they can aggregate. If you have two monomers of protein, they can come together and form a dimer, and they can form bigger oligomers. And the probability of forming a really large cluster is very small, but they will form. And those small clusters, those clusters with a large number of proteins in them, are very effective nucleating agents. There are very few of them, but they are very strong nucleating agents. So what we have measured is not the mean ice nucleating rate per protein, but per protein cluster. We can actually do gel electrophoresis, and we can in fact see that as well as protein monomers, we have got protein dimers. And if we use unfiltered protein, which we sometimes do for test purposes, you can see that there are also larger clusters. And we believe that the very large clusters are responsible for the nucleation at higher temperatures. So at higher temperatures, we have got nucleation by very few ice nucleating agents, clusters, and at lower temperatures, we really can measure, we believe, the contributions of the individual proteins. So as you change the temperature, you go from a curve where it's dominated by very few ice nucleating agents to straight lines where you have got more and more of the ice nucleating agents active. So we can actually separate the contribution to the ice nucleation rate from monomers, dimers, and clusters. And what is nice is that classical nucleation theory now explains the data very well with quite believable values of the different parameters. So no need to look at the details of this, just that the theory now does explain the data quite well, and we can separate the contributions. So can we find a better ice nucleating agent as a model than a protein? And one thing which is very interesting is to use DNA origami. DNA origami makes use of the fact that when you have got the nuclear bases that form the nucleic acid, one base always matches to the other. It's a sort of like a biological click chemistry. And this is really useful because it means you can create artificially a sequence of DNA that you know is Oxford. And you can show, in fact, that the DNA is a very good ice nucleating agent. There you see it compared to the ferritin. Okay, I do not want to bore you, therefore I will go straight to a summary of this work. Here is a summary you can see faculty. So I see a lot of applications from people. If anybody, whatever level you're at, would like a little bit of advice on how to make a good application that will be taken seriously by a top university, feel free to ask me afterwards. And the final thing I want to say is, please do not forget my 2 lessons. You can forget what I said about ice nucleation. You shouldn't, because it's really interesting, but you can. What you must not forget is to always do these order of magnitude calculations, and never, especially if I'm in the room, ever quote too many significant figures. So, thank you very much.
Bacon?